Hello, everyone, and welcome to the DSPT7 Unit 2 Build Week. I'm going to be your gracious host, Brandon, your SL. And today we're going to be doing presentations on the project that you guys have been working on for these last 2 weeks. All right. The way we're going to do this is we have a list of each student that is ready to present. Each student will be notified. We've already notified the first person to present. Next student, once that first person starts, the next student on the list will be notified. So stay on your toes. Make sure that you are ready to go with the link to your project. If you have a blog or a Plotly Dash app, go ahead and be ready to drop that link into the Slack chat and share your screen and start your presentation when it's your time to go. All right, that'll make this pretty seamless. Okay, as everyone knows, just like the Unit 1 build, we have 2 minutes per presenter. It's a hard cap, so at 2 minutes, I'll be counting down, 10, 9, 8, 7, 6. And then once time's up, I'm gonna say, all right, thank you very much. And we'll have a little bit of feedback and chat before moving on to the next presenter. Do your best, try to stay within that 2 minute mark. All right, awesome. And this goes really without saying, but I'll say it for clarity. Make sure that anything that we say as far as feedback for each of the presenters is constructive, and let's be kind and respectful to one another. Okay. All right. That being said, make sure that when you're done presenting, you remute your microphone so that we don't have to track you down. No hot mics. We don't want to hear your mom yelling at you. Okay. With that said, our first presenter is going to be Paul. So Paul, whenever you're ready, the stage is yours.
All right. So everybody can see. Okay, so I did my project on predicting rain in Australia. I got my data set from Kaggle, and originally it had a target data set. It had a target classification prediction column, but it was really unbalanced. It had 77 and 22.5%. So I actually reconfigured my target column and balanced it a little bit better, and made a new target of classification score, baseline score of 64 and 35%, which was a little easier to do. I also had some time series challenges because of seasonality, but because of what I was doing was only really for 1 day, all I really had to do was just shift the data 1 day. So that really wasn't an issue with the regular time series challenges like you normally have for a long span of time. I also had some problems with data leakage. I had a couple things in it because it was a single day. I could actually have future data leak into my model. So I had to remove a couple different columns. I fit 3 different models. First one was a decision tree classifier, and that gave me a validation accuracy of 74.87%. Then I did a random forest classifier, which gave me a marginally better rate of 75.93%. And then I also did a logistic regression model for a linear model, and that was the worst performing model, only 72.9%. I didn't really want to overfit, so I didn't really hyper parameter tune too much, but I actually ended up getting some overfitting anyways when I used my random forest model, which was my best performing model. My test data accuracy only came to 74.3%. So just out of curiosity, I actually put the decision tree classifier on there on the test score too, and it actually came out better with a 74.5%. And then I had some plots to explain some of my different things and see how they impact the models.
Awesome. And I'm gonna stop you right there. That's time. Fantastic. Let's get some emoji love in the chat for Paul. Make sure that, okay, yep, you've dropped your link there. That's fantastic. And I love that you identified, right? Because working with time series data can be very prone to data leakage, right? So that's something you have to be extremely careful with, and like that you were able to identify that. Also that you changed your target classification, right? Your classification target rather, right? When you noticed that you had imbalanced classes. So you just changed your question a little bit to better match your data. That's great. Fantastic work, Paul. Thank you. All right. Moving right along. Up next is going to be Mark Morelos. Mark, whenever you are ready, you will have the floor.
Okay, hold on. Okay, so I picked a data set from Sonoma, a neighboring county here in California. It has data from 2013 to the present on animal adoption. From the data, I've learned that domestic short hair, a cat breed, makes up about 27% of the animals in shelters. So Pit Bull, Chihuahua, German Shepherd, and Pit Bull mix makes up the rest of the top five, or almost 50%. So 46% of the pets are adopted, 37% are returned to owners, and the remaining 17% are either transferred, euthanized, stolen, or disposed of. So this gave me a 54% as a majority class, which is my baseline. I have simplified and engineered some features for my prediction model. So I've used 5 features: age, size, outcome condition, animal type, and fixed condition. I have used logistic regression for the linear model requirement, and ended with a validation accuracy of 81.75%. For the tree-based model, I used XGB classifier, which gave me an accuracy of 82% and a test score of 85%. I used partial dependence to visualize interactions with the fixed and animal type features. And it shows that whichever type of animal, if they are fixed, they have higher chances of getting adopted. So this Shapley figure was from a function made that provides reasons on the prediction, like pros and cons, as well as the probability rate. This one describes a 1.5-year-old dog, fixed, medium-sized, and healthy, being predicted to be adopted with a 51% chance. So being fixed greatly influenced the prediction, and it tells us that the factors of being fixed, young, small, and healthy can get an animal a better chance of getting adopted.
Fantastic. I'm going to stop you right there. That's time. Mark, real quick, were you showing us a graphic on your screen? Because I don't think that we're seeing it. Said here's the Shapley plot, and then I didn't. All I see is predicting animal adoption in Sonoma County.
Oh, okay. I think I was browsing on the wrong window.
There we go. Yeah, now it's moving. Yeah, okay, cool. So now we can see those awesome graphs. I had a feeling there was more to it than this, just that one picture, but I was like, I didn't want to interrupt him right there. No, it's fantastic. Okay. I like this. I like this. I like this a lot. Number one, very balanced classes, right? 54%, very balanced classes. So I feel like we're going to get a good model out of this. And good work using the XGB classifier. And I love the insight graphics as well, now that I get a chance to look at them. Age being the number one predictor. Yeah, I can see that. That's good. Yeah, so scroll down a little bit more. Let me see there. Yeah, we got a confusion matrix. Partial dependence plot. Yeah, that's good. Awesome. Fantastic work, Mark. Absolutely. This is great. Good work. Let's show some emoji love in the chat for Mark. Fantastic. All right. Up next is going to be Iskander. Whenever you're ready, the stage is yours.
Hello.
Hi. There he is.
Sorry.
Hey there.
Didn't expect to be called next. But yeah. Let me quickly. Should I share my screen?
Yeah, if you can, drop a link to your blog post or your Plotly Dash app, and then share your screen, and away you go.
There you go. All right. All right. So I decided to create basically link the data set to a personal story where I used to be a big fan of German national soccer team from 2002 to 2014. Up until the moment, basically, I was waiting for the moment when they would win the World Cup. So I used that experience to find a data set that would perfectly describe, in a way, would describe the variety of events that happen in European soccer leagues, to an extent where I could predict whether a shot from a certain location, based on a certain precedent, like predicate event, whether it's a pass or a fast break, would result in a goal. I created two models. They use the XGB classifier as well as a logistic regression. The XGB classifier for this particular data set resulted in it accurately predicted whether a shot is a goal or not 91% of the time, and obtained an AUC-ROC of 0.81. The only problem was that this particular data set is imbalanced, because for every shot, for every 100,000 shots, you may get just a couple thousand goals. So that resulted, that required me to change a metric, and so I decided to go with the AUC-PR, precision recall, and achieved a good level of good score for AUC-PR as well as Cohen Kappa.
All right, and Iskander, I'm gonna stop you right there, man. We're at time.
Sure.
Fantastic. Yeah, it looks like you had a lot to dissect there for us, but great work overall. I also particularly enjoy the fact that you recognize that you had imbalanced classes, and the way that the data was structured, the best way to approach that problem was going to be changing your classification metric. That's fantastic, right? That's an absolutely 100% valid way of dealing with that type of problem, right? So yeah, you're just basically changing how you're describing the performance of your model without actually changing the way the model performs. Fantastic work. Awesome. Definitely want to give this a more thorough look over though, so make sure you link that in the chat, and let's show some love for Iskander. Fantastic work. All right. Up next is going to be Joanne. Joanne, are you ready?
Okay.
Don't forget to link your project in the chat. And
yeah,
the floor is
I
yours.
just down there.
All right.
You see it?
Good to go.
All right. For my project, I wanted to know what would be the most seen shape of UFOs in the future based on data collected for real-life reported sightings. I started with a data set that contained over 80,000 observations and 11 features. The first thing I did was look at the frequency of the years, the frequency count for the years. That is when I found that there were not many sightings prior to 1994. So that helped me to reduce the number of observation in my data set I would go on to use for my predictions. I decided to use the data from 1994 to 2014. And that reduced my observations to just over 72,000, which is still a lot, but then the target feature that I decided to use was originally called shape feature. which was divided into 30 different shapes, including the NaN values. So I created my own feature and named it shape classes, which only had 6 classes to break down the dimensionality. And then I did some processing, but did some exploratory data and some processing. And I'm not going to go into depth over all that because of time constraints, but you can see it there. It's all on my blog. And then I just did a little visualization to show some of the data that I used for predicting on. And then my baseline score was actually rather low at only 31.86, but this is probably because I had a multi-class target feature. And they were sort of balanced out for the most part. Then I did some logistic regression. And with my logistic regression, I tuned some of the hyperparameters. And I got a train accuracy of 31.78%. And I got a validation accuracy of 31.88%, which my validation accuracy was actually better than my train accuracy. And then when I did it on my test accuracy, once I decided on my hyperparameters, I ended up getting a 32.8% accuracy, which is slightly.
Perfect. I'm going to stop you right there. We are at time. Yeah, 2 minutes goes by super fast, I know.
Yeah.
This looks really interesting, but I have a question.
Yeah.
One thing that I didn't get from this presentation was, what was the most determining factor for the type of UFO sighting? Did you find that information?
As far as feature importance, or I also did permutation,
Well, yeah,
feature importance.
Yeah, exactly. Which one was most? Okay, so it looks like hour was the highest weighted feature. Okay, that's interesting.
Which was rather surprising to me, actually. I didn't expect that to be the most important feature, but then again, after doing some thinking on it, it kind of made sense to me, because the highest target feature was actually a type of light, so that would make sense.
Right. Yeah. Because I'm thinking, later in the day would definitely be right. A big thing about. So, but yeah, later in the day, more likely to be a UFO sighting, and a type of light would typically only be visible at night. Yeah, that makes sense. Okay, so that kind of matches intuition. So yeah, this seems like it was a kind of a time series problem. So I'm curious about how that affected the way that you went about engineering your features, but I love that you devised your own sort of concatenated, or rather truncated target list, right? So you took it from a bunch of different types of the same basic geometric shape and then summarized them all to give yourself less overall targets. That is a really good way of simplifying an issue, right? Or simplifying a problem. That would probably make it a lot easier for the model and probably benefited in higher accuracies. Great work, Joanne.
Because otherwise it would have been really bad on the scores.
Multi-class classification is tough, and we're going to definitely hit a little bit deeper on that in neural networks, right? Different ways of handling multi-class classification.
Right. Thank you.
You got it. Fantastic. Thank you so much. All right, next up is going to be Yinmi. Do we have a Yinmi?
Yes, I'm here.
Awesome. All right, Yinmi, whenever you're ready, go ahead and link your project in the chat, and the floor is yours.
All right, how you doing, guys? So I will talk about early stage diabetes risk. This data set can be found in UCI machine learning repository, is and about 422 million people worldwide dies already and have diabetes, and 1.6 million dies already. So the data set has 17 columns and 520 rows. I will talk about I will use classification models like logistic regression, decision tree, random first classifier, and XGBoost. So let's go with the baseline. So here's my baseline on 61%. Let's see if I've improved with these models. So this is my validation accuracy and my test AUC for logistic regression. This is my confusion plot. Matrix plot. This is how a confusion metric looks like, and what is the TPT and FB and FN means. Also, I got a classification report for logistic regression, and this is how classification report works. Precision formula, oh, oh, the recall, the F1. So what is loop? Hang on a second. This loop like smooth. Wow. Well, permutation importance. This is my permutation important. Permutations means the features that help you with the feature depends on the models. This is my decision tree model with the accuracy, confusion matrix plot, classification report. This is decision tree model visualization.
Okay. Yenmi, I'm going to stop you right there. We are at time.
Okay.
So, yeah, I think you did a lot of great work here. During your presentation, I kind of felt like I was being taught what precision and recall was, and less understanding kind of your approach to this particular problem. All right. What I would have liked to have seen a little bit more of in this presentation was your thoughts and your process working through predicting. I don't know what your target metric was actually, so I don't know what your target was. Can you actually walk us back real quick? What was the target that you were trying to predict with this data?
Oh, I didn't move it too fast. It's class. If
Okay, so does or does not have diabetes?
yes, if negative or positive.
Okay, so yeah, this is like something real world that impacts millions and millions of people every day, right? So like a really important area of research, right? And helping to understand what factors lead to or might predispose you to a higher risk of diabetes is definitely important, right? There's like tons of applications for that. So would have liked to have seen a little bit more of your process in devising a model, right? To get the best predictions using this data. Okay. Now, that's not to say that I don't love the details that you walk through, like dissecting your model, right? The confusion matrix looks good, and it actually looks like you got a really well-performing model. I just would have liked to have seen a little bit more about how. Okay?
Okay.
But great work. Thank you very much for sharing this with us, okay?
Oh, you're welcome. Thank
awesome. Let's show some love for Ian me in the chat, y'all. Make sure to check out his blog post. All right. Up next is going to be Thomas. Thomas Shorts. Are you here with us?
Yep.
Awesome.
All right.
Whenever you're ready.
Yeah, just going to share my screen, drop the link in the chat.
Awesome.
Wait for this bar to go out of the way on the top. There we go. All right. So I did my project on trying to predict whether or not a baseball player will be inducted into the Hall of Fame on their first ballot. I've seen it done where people try to predict whether or not they'll be inducted, but you have 3 ballots to be inducted on. So I figured I would shoot for the moon here and try and go see if we can use stats alone to predict whether or not they'll be inducted on the first ballot. We used 3 data sets here to kind of construct a data frame where we had 1 entry for every first ballot with some select stats that were available for computing, such as batting average, and then some other categorical ones like number of seasons played. I decided to bin that. Data cleaning was kind of a pain for this. There was a lot of missing data. Pitchers were included in the list, so I had to decide at some point to pull them out because their offensive stats wouldn't be conducive to predicting whether or not a player would make it in. So I just narrowed it down to position players. And that gave us 771 entries with an incredibly skewed target of 95% no and 5% yes. So since we might have some monotonic relationship with things like the year they were inducted, certain things like that, I decided to go with a random forest. This is the first one we did here without SMOTE or any hyperparameter tuning. And for the amount of positives there are, we actually did pretty good. We got a validation precision of 85.7, a recall of 75, and an F score of 80. But that still doesn't beat the 95% precision of the majority class baseline. So that's kind of hard to beat. Next thing we did is we used SMOTE to increase the ratio of our yeses to 0.5 here. And you can kind of see what that does to the data. This is just a look at the distribution of career hits. And you can see that it inflates the number of things you would expect to be a yes, where players have 3,000 hits here. So at this point, you're thinking, great, we've got more data. We're going to have a better metric. Not actually. Our metrics actually went down to a straight 75, 75, and 75 here on precision recall and F1. We compared them here. Got some ROC curves. Basically, first model is more generalized. The second model has higher precision in the middle thresholds.
Outstanding. Okay, fantastic. Thank you, Thomas. A lot to talk about here. So, yeah, you were trying to predict something that inherently it sounds like is very rare, right? That is a perfect example of anomaly detection, right? You're trying to find the cases, or you're trying to find those features that indicate that something rare might occur, right? Something that doesn't happen very often. That's a hard thing to do, especially with non-time series data. I've only done it with time series data. So I applaud your efforts. I think you did really well. With that first model was pretty generalized. So real quick, why do you think the second model, when you increased the number of observations, right, to more evenly spread your distribution of target, why do you think that second model performed worse than your first?
It performed worse based on precision, I think, because it increased the recall by kind of it gave the model more borderline cases to look at, I think, or not enough borderline cases, something to do with that. And I noticed it increased the recall and decreased the precision.
Yeah, especially with a random forest model, they're already predisposed to overfitting. And I think what happened was because you have so few cases of positive indicators, that certain features ended up getting weighted much heavier when you had even more observations.
It was definitely a brutal learning experience.
Yes, I bet it was. But that's awesome, right? It definitely showcases a lot of your process, and I think it's fantastic. Great work.
Thank you.
All right. Up next, we have Sarah. Sarah West, are you with us? Sarah, you might want to check to make sure you're not muted. I think you might be muted.
Okay. I started out with a data set about who's going to default on a loan, and didn't realize that such extremely imbalanced data is not the best fit for a newbie. And I learned about downsampling and applied it incorrectly and downsampled all of my data, so I was way behind at a point. Anyway, downsampling is when you take the data and you cut out a bunch of your majority class to match up with the minority class. I only had 2.18% defaulters. Prior to downsampling, I ran it through my models and did not catch a single defaulter. And then when I did it with the downsampled data, it got somewhat better. And then I tried synthetic majority oversampling, which is creating a bunch of fictional defaulters, and that improved it more. And then I used the ROC curve to perfect my model, though now I realize that wasn't the best curve. And in the end, I had my logistic regression model with the curve giving me the best outcome. So I got 0.54 for the recall on my defaulters, and a 0.63 on the non-defaulters, which means I would be telling the bank that 38% of their people are going to default, which is not particularly useful. And here is my confusion matrix, which shows you the numbers here. So these are correct, and these are all the poor people who are not defaulters that I thought were. So because my model wasn't particularly good, I chose a version of it to pretend with so I could do some Shapley values. And unfortunately, we can't zoom here, but we have a male about 40 years old who is self-employed, and he wants to take out a loan. And the bank is going to say, we're so sorry you don't have a history of taking out unsecured loans. We don't like where you live, or we do like where you live, one of those two. Anyway, there's a number of things that contribute that the bank would find useful to tell him.
All right, fantastic. I'm gonna stop you right there. We actually ran a little over because I was so invested in your story. Right, I think this is fantastic. Definitely highlights some of the complications, right, with highly imbalanced data sets, as we were talking about with previous presenters. And sometimes that's not a very easy thing to overcome, right? Sometimes you can find some gimmick, but sometimes you can't. And that just means that maybe we don't have enough data, right? Maybe there's something that we're missing from this calculation. And that in itself can be just as informative as a predictive model that's getting super high accuracy. All right. So I think that what you've done here is not necessarily a waste of time or effort, right? We can definitely glean a lot of information from this, given more time to dissect. But I especially love that confusion matrix. If you scroll back up, we can see that the model was definitely heavily skewed toward thinking that they were a defaulter when they weren't. By it looks like nearly 60%, just over 60%, I think, of the time, right? So the model is definitely getting very confused there, and I would be interested to see they kind of dive into the features and try to see like where most of those miscalculations are coming from, because I bet we would find a trend in there somewhere.
This also was somewhat confusing because it was people who had a loan and they were getting a second loan and they couldn't tell which data was supposed to apply to what.
Right. Now, I do have a question though. Did you try attempting fitting a like a random forest or other type of
Yes.
classifier?
I tried the XGBoost.
Right. Okay.
And the logistic regression, and
did they have any different? Okay, yeah, not much better.
There's a difference. It's not a little better here.
Gotcha. Okay. Yeah. No, that's great. That's really telling. All right. It says something about the data, and it says that this is pretty hard to predict, right? For one reason or another. Okay. Awesome. Great work, Sarah. Thank you. Let's show some love for Sarah in the chat, and we will move on to the next. Next up to present is going to be Adam.
All right.
Adam, are you ready?
I am.
The floor is yours.
Okay. So for mine, I decided to make a web app with the basic idea being that you're trying to predict times for competitive swimming based on the age of the athlete, the gender of the athlete, and other times that the swimmer has done in other events. So I'll just run a quick demo to show you how it works. You'd enter the age, the gender, then you'd add that, and then you add a swim. So I'm going to add a few quick events. So you'd add a time, and then just to make it real quick, I'm going to add just 200. So you'd add the times to the app, and then as a user, you'd select which ones you wanted to use in a prediction for an event. So you have to choose an event you want to predict for. So I'm going to go with the 100 breaststroke. And you have to select one first. So you can use, it uses the information you selected as well as your age and gender to predict. And then it gives you back an estimated time for that event, as well as some information, as well as some data that it uses, which is basically from the database. And if you look at the information, you'll notice something that seems out of the ordinary, which is these corners at the top. And the corners at the top because I had to actually go to the USA Swimming database to get all the times. And as it turns out, there are way more times that exist than I got. So at some point, it cut off how much was available. So you can also add another event. It's an additional feature, which will include in the prediction. So it made the time go a little bit down. And there's also an about section, which explains what's going on under the hood a little bit, what it's for, how you would use it. And here are all the different events that you could possibly have for a swimmer. So any swimmer is bound to be missing at least like most of these events. If you want to predict, you can only use the ones you have where the green check marks are. And so behind the hood, there's
All right.
All right, we're
Real
done.
quick. Yeah, real quick. Yeah, 2 minutes is up.
All right.
Man, this is fantastic. This is absolutely fantastic. I love this. I especially love that while you had a background data set that you used to train the model, adding the ability to add in new times to, which I'm assuming is retraining. Is that retraining your model in the background?
So what's going on in the background is that you're right, I'm retraining a model, but see the way the database works is it has to select only observations where individuals have times in those events. So it has to select only a certain subsection of the database. And then after that, it then trains on that section of the database.
Okay.
So it does have to retrain.
Yeah, that's really interesting because that is something that's basically you've developed a pipeline, okay, to dynamically retrain models based on user input. That is highly advanced. Fantastic work. I applaud this. Definitely interested in looking into this a little bit more. That's great work. But yeah, just all around. Awesome. So let's get a round of applause and some emoji love in the chat for Adam here with this awesome swimmingly. He even named it. That's so cool. All right, cool. All right. Up next is going to be Luke. Luke Melto, are you here? Did I say your name right? Luke Melto. Now I'm thinking about melt, so now I'm hungry. Whenever you're ready, make sure you're unmuted. The floor is yours.
Hey, can you hear me?
We got you now.
Alrighty. So for my project, I was predicting tornado intensity classes. So I'm working with the F scale, which is 0 through 5. And I got my data from the National Weather Service and NOAA. So I have 6 classes, F0 through F5, and this is extremely imbalanced data. So that presented a lot of challenges that I'll go over in a minute. So starting off with the baseline, which is F0 is coming in at 46%. So with these imbalanced classes, if I could beat that, I'd be happy. Starting with my random forest model, I was able to get to 66%, which is a decent accuracy, but as you can see from the confusion matrix, it's just not very good recall. It's not predicting the classes with any certainty at all. So looking at some of the columns, the feature importances, you can see that latitude and longitude are the 2 strongest. But if we actually look at what is defined in the Fujita scale, it is measurement of a tornado's destruction on man-made structures and vegetation. So I ran a version of the model only looking at destruction, crop loss, injuries, and fatalities, and ended up with 62%. So lost a little bit. It was kind of just an interesting experiment there to see that there are other factors that can provide value, even though the scale doesn't look at those specifically. So looking at what I could do to increase the accuracy of these minority classes, I used SMOTE and near miss and ended up with about 63% accuracy and much better recall.
Fantastic. And that's time? Yeah, so, okay. Early on in the process, it looks like that you did some experimentation, did some iteration, and maybe saw a little bit of changes, right? So yeah, one of my intuitions, though, from my limited knowledge about tornadoes, latitude and longitude, some areas geometrically or geographically might be more predisposed due to certain existing weather patterns to have like higher strength tornadoes or lower strength tornadoes. So it kind of makes sense, and I can see how that definitely played a role in your model's predictive capabilities. But then it looks like you did SMOTE, so you did some oversampling. and that definitely helped. One of the things that I'm really kind of interested in is its predictive capability on F5. It seems to be very confident in
Yeah, it
being able to
does.
predict a high
It's
level
good at
tornado.
both ends of the spectrum and average in the middle.
Yeah. So I would wonder that maybe you could rephrase this question instead of making it a multi-class classification where you're trying to predict the exact F scale of each tornado. You could divide it into two and make it a binary problem. Is F5, is not F5, right? Maybe, because depending on the problem, maybe you're only interested in it being a highly destructive tornado. So F4 to F5 versus mid-range and lower, F3 down to F0, right? There's a ton of ways that you can turn this into a different problem and maybe get a better predictive model, right? So it really just kind of depends on what the question is. But I love the work. Fantastic job. Great execution, and it all came together. Fantastic work. Show some love for Luke in the chat. All right. Next up. Okay. Next up is going to be Cortez. Do we have Cortez?
Hey, what's up?
What's going on? You're going to be next to present.
Okay, cool.
Whenever you're ready.
Okay, so what I have is called a predicting transparent devices. It's basically using a dash bio to visualize these molecules and predicting if something is a good insulator or conductor. And like in our current devices, we have something that is gold that looks like this, usually in our devices, while transparent molecules will be made out of like indium, gallium, aluminum, and oxygen. And I use something called like a vector, what is it? Support vector machines to find the band gap. And the band gap is basically like to see if something is more a conductor or something is more of an insulator. So the way how support vector models go, they kind of like, it uses like categorization techniques on linear regression. And so like our vectors are the red things, and then they find a decent medium, and compared to a typical linear regression, we are able to find 7 different trend lines instead of just one. Here are my metrics. Like my baseline for MSE was about 0.90, wait, baseline, yeah, 0.83 for band gap. And so use metrics. I think like I started with like a linear vector model with just 0.72 R squared, but like since these crystals aren't linear, then I made like used polynomial headers, so hyperparameters, so it's more accurate at 0.96 R. So, and here are my metrics. And I also made like a Plotly Dash app, which it is interactive to find this sort of, the conductor and find the insulator.
Fantastic. So I'm going to stop you right there. That's time.
Okay.
I'm a little blown away. This
Okay.
is definitely above and beyond.
Okay.
Specifically, I absolutely loved that you used a machine learning algorithm, unsupervised learning, to assist your supervised learning. That's fantastic.
Okay. Cool. I didn't know I did that, but okay.
So yeah, if I'm understanding the problem here correctly, you're trying to take a molecule and various properties of that molecule and determine if it would be transparent. Is that right?
To determine if it is more if it's better conducting electricity or insulating electricity. So like
Okay.
This is an example of a good conductor. It looks like it's flat, and here is a example of a good insulator. It's pretty big and bulky. So
okay, interesting.
It's just how electricity flows through it. Yeah.
Right. And does the SVM directly give you the conductivity rating?
Yeah. I had a hard time. Like it's like in order for this to plug it in, I have to scale it down, and
Mhm.
so I haven't scaled it up yet, but it's a scaled down version.
Okay, so I got that a little wrong. I thought you had a supervised model where you already had the outcomes
Okay.
known, like if it was conductive or not.
Yeah, it
Um,
was known except for like the train model. Yeah, like the test model that was like.
okay. Okay, so okay, gotcha. That's fantastic. And this is just another really good application of clustering then,
Cool.
even on a supervised learning problem. This is fantastic. A lot of
Cool.
great work. Yeah, I was a little concerned when I saw your data though. I was like, that's a lot of very complex data. But I love what you've been able to do with this. I especially love these interactive 3D models. That's really cool. If you definitely link this in the chat, and I would be very interested in learning more about how you did all this.
Okay.
So if you have a blog or something on that, I would read it.
Yeah. I was planning on making like a separate tutorial on how to make VMRs since there's not really a lot of documentation on how to do it. So something like that would be like a lot useful for like when I need to do it again.
Yeah, no, that would be really fantastic. Thank you.
Cool.
Great work. Let's show some love for Cortez in the chat. Awesome. Moving right along. Next is going to be Timothy. Are you ready?
I am.
Fantastic. Go ahead and drop a link, and the floor is yours.
Right, the link is out. All right, using machine learning to predict dying stars in our galaxy and beyond, and more specifically pulsar stars, since they seem to be the most useful for space exploration. I go a little bit into what pulsars are. If you don't know, please feel free to check the blog and read. But why do Earthlings care about pulsars? Specifically because using pulsars as a set of lighthouse beacons, a craft could determine exactly where it's positioned in three-dimensional space. A little bit better than the Deep Space Network can do because it only shows distance from Earth. Some pretty cool pictures and onto the data science. I break it down how I split the data. I check Stratify works, as we know it does, but I explained that a little bit as well. Also into my test and train vector and, excuse me, my X test or X train and sets and Y vectors. And then I go into random forest regressor. First model gets an 80.3. Not so great because 80.4% is not as good as the baseline, which in this case is about 90.8%. So it's not useful for this use case. Then I go into logistic regression. It's kind of upset me because I did this model last because I didn't know we needed a linear model, but it tied my best hyper parameter tuned random forest classifier that I spent a bunch of time trying to figure out. Still though, improvements can be made. I'm going to try for better accuracy score for science. Love to see another, yeah. There's a couple quips you can read if we have time. And then I did a confusion matrix on both of my random forest classifier, and then our ROC AUC curve, checking all my accuracy scores here, and then I go just a little bit further with XGBoost classifier. I drop my false negatives down to 47, false positives down to only 10, and check the last of the metrics. Then it goes on to test my accuracy, XGBoost wins, and I have quite a bunch more plots here if you want to check it out.
Fantastic. I'm going to stop you right there. Some more awesome visualizations. Love to see it. So yeah, I'm a little biased. Anything astrophysics I love. That's my jam, for sure. And yeah, having worked with a very similar type of problem before myself, I'm curious to know what was your baseline for the data set that you had trained this model on?
It was a 90.8% not pulsar. So if I would have guessed, everything was just not a pulsar, then it would have been right 90% of the time. So my ending accuracy got me really close to 98% with the XGBoost after all the shooting I could do.
Exactly. So given that you're all right, so the only thing that I would change, right, if I had to offer any criticisms, would be that given that your baseline is 98% for accuracy, you might want to instead choose to evaluate your model on something different, like your precision or your area under precision recall curve, even. Because that will speak more to how well your model is differentiating pulsars from non-pulsars. Does that make sense?
Yeah, it does. And I did go into that. I didn't really speak on it in the explanation because I
Gotcha.
but in the blog post, I do talk about how the final ROC, AUC curve, and precision both have gone up without any drop off to recall or F1 scores. So that's why I go with random forest or the XG boost in there.
Fantastic. And another great point to make that I love that you found this, right? Because we always have to learn, right? Sometimes the simple model performs just as well as the hyper complex. Build the skateboard first, not the car. You might save yourself some time. So I love that you were able to learn that. And I'm interested that it performs so well. It's very interesting. But yeah, fantastic work. Let's show some love for Timothy in the chat, y'all. And definitely link that. I am interested in checking that out later as well. All right. Guys are making great progress. We're almost halfway through now. Up next, it's going to be Megan. Megan Felker, are you here?
I'm here.
All right, whenever you're ready, the floor is yours.
Okie dokie. Is it loaded?
Let me just start by saying I love this picture already.
Thank you. Took a lot of time to make. Might have wasted too much, actually. So my blog post is going to be about essentially my entire process in predicting the birth counts from the data set that I used in my last build. And I think that, at least I learned that continuing from data that I already knew helped a lot because I knew where a lot of problems were in advance. So I knew where to get rid of a lot of them. So the data cleaning process of this was very quick. So I put that graph there to show why I chose births, because the fertility in the last build had uniform, so did the population, but births kind of has its own system. So that made me curious, and that's why I chose to make it my target. Oh my gosh, my hand. So I make a dictionary because I planned on using a lot of words that average Joe wouldn't understand. And I then went on to define my features so that, again, I didn't think that average Joe would understand that. Sorry, my hands are shaking really bad. And that's, oh my gosh.
You're good, keep going.
Thank you. So there's a lot of Star Trek references. I love Star Trek. But I do make a comparison between machine learning and how the process works a bit like space exploration. So it wasn't completely random. My baseline model was used on a linear regression, and because of that, my regression metrics for my R2 score for my regression, I can't find it where I'm at. My R2 score was a little bit high, my baseline. Right, there it is. So it was a bit high, and I try to explain why I use the metrics that I use, because it's a lot of them, and I do use all of them in a way. Okay, well, I'll just scroll through in these last 10 seconds to give you guys a bit, because there is quite a lot of information in this blog post. But essentially, I do find a model that can predict, and I do apply it to something that I could actually use, which is a fictional world and predicting the amount of births occur in that world. And that's the map of that world.
Okay, hold up. That took a turn. So I was not expecting that, and that is interesting. So I'm like 100% more interested already. Okay, so you used real-world birth data to try and predict what the birth rates would be in a made-up world? Is that correct?
Yes. Yes.
That is interesting. That also sounds like a problem that would have a lot of real-world application as well.
Yes.
So that is very interesting. So obviously, a little critique for you. There was a lot of breakdown in that presentation. I would advise maybe just work a little bit on your pacing, right? The visualizations themselves were fantastic. I loved them. High in contrast, easy to digest. I looked at them and I pretty much understood exactly what they were. The only critique that I could have maybe is with that first graph, having a whole bunch of numbers like that can be a little hard to understand what I'm looking at. So some healthy abbreviation might help there in those cases. but everything else was fantastic. I love the use of color, right, to kind of bring some life to it. So that was fantastic. Great work, Megan. Thank you.
Oh, thank you.
All right. Well, up next is going to be Zachary Snyder. Zachary, are you here?
Yep, I'm here.
Fantastic. Whenever you're ready, the floor is yours.
All right, so I did my project on the same data set I used for Unit 1. So it was the Kiva lending data set. So basically a data set, kind of a crowdsourcing site to match borrowers and lenders for small businesses in developing countries. So the business question that I got out of that was I wanted to predict what loan amount you were likely to receive based on a variety of factors like where your country was and things like that. So I used root mean squared error as my metric because I wanted to kind of get rid of those outliers and punish those a little more harshly in my model. So that, because if you try to get something way too large, it's more likely that you won't get any loan at all, rather than kind of closer to the actual amount. So the baseline, I got a score of 0.95 logarithmic dollars and 1.8 for the test set. So then I made a linear regression model next and improved a little bit, got 0.84 for the validation and 1.7 for the test. Then I kind of looked at the coefficients because it's easily explainable. That's the kind of the best thing I got out of the linear regression, and found, for example, that as your term in months goes up by 1 month, you get a increased predicted loan amount of 0.16 log dollars for your loan. Then I went with an XGB regressor model as my kind of final, more complex model, and improved on my score quite a bit. Got 0.44 for the validation set and then 1.3 for the test set. Then I have some explanations down here. I looked at the permutation importance and found that country was the biggest factor, followed by gender, which kind of makes sense intuitively because if you're in a country that it takes less to buy things per dollar, then you would need less of a loan amount. Then I looked at a PDP plot for term in months, and then I looked at feature importance as well.
Sorry about that. Yeah, I'm gonna stop you right there. We're a little over time. Again, I was highly invested there. So this is really cool. I like the work that you did. I especially like that you took the time to explain why you picked the metric that you did. Right. So understanding the intuition behind how you decided to evaluate your model helped me to have some context as you went forward in the explanation of your model. It's fantastic work. Thank you. All right, let's make sure to show him some love in the chat, y'all. Next up is going to be Keith. Keith Turman, are you here?
Yep, one sec.
All right. Whenever you're ready, link that project in the chat, and the floor is yours.
Okay, so you can hear me, right? Everything's good?
Got you loud and clear.
Okay, so I'm looking at loans. I'm trying to see if it's possible to predict who is more likely to be late and who isn't. In this case, late people are pretty much 30 days or later on their loan, and the baseline for those that aren't late is around 62%. Usually when you think about loans and like mortgage and credit cards, it's usually just based on credit scores, but I wanted to see if it's possible to see if we can find any prediction from age, gender, income. And the data itself is around 440,000 people. And it also looks at if they have a home, if they have children, if they're employed, and how long they've been employed. First thing I did was logistic regression. That wasn't very accurate, so I pretty much just moved on to this random forest, which was a lot more predictive. It had better false positive, true positives, true negatives. Everything was much better from that. So I moved to this. You could see the features, which are age and amount of income, which is salary, years employed is high, gender is high. So I decided to look at age and salary to see if there's any kind of disparity in it. And it's pretty interesting because you see that the highest earners are actually the highest to have a problem paying their loans on time. The higher number here is the more likely to not have a loan paid on time. So lowest income, highest income, and youngest are all having the same problem. Gender, females actually have lower likelihood of defaulting, except some are a little off. In conclusion, it's pretty much hard to tell who is going to be late except for the oldest or the youngest people. The mid earners and mid ages are pretty much close. You can't really tell the difference. That's it.
Perfect. Then that's time. Awesome. Great work. So I'm seeing a pattern here with these loans, in that it seems like it's inherently just very difficult to tell if someone's going to default or be late on a payment. All right. And it was good to see. So you try to take this from a perspective, not with time series data, right, like of payment history, but just off the bat with some basic statistics about a person. So taking some demographic information and trying to make that assertion. Yeah, it seems intuitive that would be very difficult to do so. So I think you definitely arrived at the right conclusion there. Though we did find out something interesting, right? Like I did not expect that the highest, individuals with the highest income would also have just as much, likelihood of being late on a payment as those in the lowest income bracket. So that's definitely interesting. All right. Fantastic work. Thank you, Keith.
Thanks.
All right. Show some love for Keith in the chat. And up next is Alif. Did I say your name right? I'm so sorry if I butchered that.
Yeah, that's true.
All right. Awesome. Whenever you're ready, the floor is yours.
Okay, hi everybody. Today I will talk about the severity of car accidents in the United States. I have a data set with 3.5 million observations with the 49 columns coming from 49 states in the United States. So let me go a little bit down. Okay, so my target column is the severity of car accident, and it has two classes: high severity of car accident and low severity of car accident. I used 4 different classification models in order to get the best accuracy score on my validation data. So based on majority class, 68% of car accidents are low, and I choose accuracy score as my evaluation matrix. So the best score I got on my test set is 67% accuracy score with the random forest classifier model with hyperparameter optimization. Also, I want to talk about my permutation importance. So as well, based on this graph, I could say I have at least 10 important features which affect my predictions highly. So if we look at these partial dependent spots, for example, let me go. Oops, I don't it up. Okay, so traffic signal 0 has much more effect on my prediction model, while traffic signals 1 has less effect on my prediction model. Also, I would like to move the heat map with the traffic signals and R differences. As you can see, there is an increase in the severity of car accident if there is no traffic signals here. And also the increase in the number of R's is another factor to show its impact on the severity of car accidents here. And thank you for listening to me. That's it.
Perfect. Right on time. Fantastic. This is really good. You had a lot of data to work with. And I think that you definitely got a pretty good model out of this. If I'm understanding correctly, you were trying to determine, or rather, you had a binary classification problem with the severity of the accident being what you were trying to predict. Yeah, so that's going to be inherently pretty tough. So I think getting the scores that you did was probably pretty good, and I would definitely be interested in reading more about that.
Thank you.
Thank you very much. Fantastic. All right, so let's show some love for Leaf in the chat. Up next is going to be Haroon. Haroon is not with us today, so he has pre-recorded his lecture. So Isaac, whenever you're ready, if you want to get that loaded up for us, and we will watch his presentation.
I've got to give Zoom permission to my Mac.
No worries. Are you having, do you have sound on your end, Isaac? I don't have sound. Yeah, I'm not hearing anything. Did you share with share computer sound enabled? Stand by, everyone, while we sort out technical difficulties. All right, if you want, Isaac, I can try to do it on my end. I'm pretty sure it will work. It did last time I did this. So let me pull it up real quick, and I will attempt to share it on my screen. All right. Please let me know if you can hear the.
Right. Our question we are working over here is: are mushrooms edible or poisonous?
Does everyone have sound? Everyone can hear? All right, perfect. All right, so let's watch Haroon's presentation.
We got the data set from the Kaggle with more than 8,000 observations in it and more than 23 features, including the problem feature. We use two models in this one, which is logistic regression and random forest classifier. First of all, we check the data balancing on our data set, which looks pretty much distributed data, so we'll be considering it our baseline. We will be using 4 features: order, bruises, population, and the habitat. And after using these 4 features for our logistic regression, we reached to 77% of the accuracy score on our validation data set and 99% accuracy score on our validation data set from the random forest classifier. Then we applied both on our test sets. We got 79% accuracy on regressor and 99% accuracy on the test set from our random forest classifier. Both of these are the confusion metrics for our logistic regression and random forest classifier. Conclusion number 1 is that because our problem over here is a classification problem, that's why the result of the classifier is much better than our regressor. So we'll be digging deeper into our random forest classifier and took one observation from our test set to see the result with our shape force plot. For this specific observation, our result is 73% accuracy, and see how these 4 features contributed to get to this 73% accuracy result. Next one are the 4 plots, which are also shape dependency plot, in which we see that the habitat feature work closely with all the other features to get to the model result 99%. Last one is the validation curve with our random forest. Over here, in our case, there is only little variance in the combination of feature values and the labels. This means a small sample size is allowing a model to find all the detectable patterns, resulting this early high score with our random forest classifier on our data set. And that's it.
Oh, here we go. Okay, so that was the end. Awesome. I know he's not with us, but I'm going to give some feedback on that. He had said this was really great. I think that the model's predictive capabilities with the random forest was fantastic, right? Clearly a very well generated model and highly predictive. With the logistic regression, so at the very end, he made a good point, right? He talked about something that we haven't seen too much of yet, and that's feature interaction. And one of the things I want to point out is just because the logistic regression has regression in the name, it is not a regressor. It's not a regression, right? It is a classification. It's called a regressor because it gives out a probability in the form of a real number, right? So that's a number between 0 and 1, and it's some decimal there in between, okay? But we use that to get a classification, right? 0 or 1. That being said, I think the reason why the random forest performed so much better is because it was able to, pick up on nonlinear and non-monotonic relationships in the data, right? Because of all that feature interaction, the linear model wasn't able to pick up on those key tells and get that same predictive capability. All right. Otherwise, that was a fantastic presentation. So let's show some love for Haroon. Even though he's not with us, he's with us in spirit. That sounds awful. Okay, moving on. Next up is going to be, is Rose with us? Rose Wachera?
Washira, I'm here.
Wachera. Oh, hi. Yes. Perfect. Whenever you're ready, the floor is yours.
For my project, I kind of focused on hospital readmission for patients with diabetic. The main reason I did this was because my dad is a diabetic, and most of last year I was hospitalized because of different procedures. So I wanted to kind of dig deep into this and see what I can learn from it. So I got my daughter from UCI, what was between 1999 and 2008. I did several data preparations that I have listed below. And my target was to find out the readmission. So for anything that was satisfying this, the length of stay, medication, and procedures, those were the features that I included in my data, in my model. So my target was readmission. They had two kinds of readmissions. That was either after 30 days or greater than 30 days or no readmissions. So I wanted to do because this is an old data set, I decided to do try to see how many readmissions were done within either for all the within the 10 years, how many people were readmitted in hospital, whether it was after less than or more than 30 days. So because there were 3 classes, I joined the 30 and less. And so my baseline became 53%. And from that, I was able to do logistic regression, which had given me accuracy of 62. I also did a random forest. And this was what I got from all my comparisons. And its accuracy score was 63. And also, I was able to find my feature of importance, which were the most important was the number of lab procedures. And that kind of agrees with what my dad went through last year and the medications that he was taking, which is kind of true. And also I did the permutation, but in this case, the top one was the number of inpatients. Also, I did analysis of all my models and—
All right, Rose, I'm gonna stop you right there. We're a little over. Yeah, perfect. Great work. I absolutely love these visualizations. And this is another one of those. So, another project involving something that is real life and very impactful to a lot of people. So I applaud it. Great work on this project. I love that you were able to change your baselines around, right? Change the question and change the answer, right? So by changing your target, you were able to get a more balanced class distribution and probably a better model out of it in the end. Fantastic work. Thank you. Make sure to drop the link to that project so we can check it out later. All right. Up next is Dustin Stringer. Dustin, are you here? Yes, you are. All right, whenever you're ready.
So I decided to make a app using Python's Flask framework, which was a challenge all in itself. And I chose to use automotive accident data to predict the injury severity of a car accident. So here's my input screen where you can see I have asking questions about the features like, does it have an airbag? Is the occupant wearing a seatbelt? The age, when the occupant got the license, a few other things that would be important to know. When we hit submit, it's going to go ahead and give us a prediction on the injury severity. Any second now. And here it's going to tell us that the injury severity is low. And we have a PDP Shapley plot right here showing that what contributed the most to this prediction was the fact was when the occupant got their license and the seatbelt. And also some of the data I chose to exclude was sex because of ethics. I read that it's good to exclude gender so that your model isn't biased towards gender. That was one thing that I chose to make my model a little better. And here I did a partial dependency plot for the feature that had the most impact in isolation, which was speed. And this shows here what it was on low. This shows what it was on medium. And this shows the impact on high. And here are just some notes about the process. The data was loaded with data leaks. I had to get rid of about 5 features in order to get rid of all future outcomes in my data. And down here, I have 2 confusion matrices of the top one is the random forest classifier model and its accuracy score. And the bottom one is the logistic regression model, which was way worse.
All right, and I'm gonna stop you right there. Thank you, Dustin. So this is fantastic. I love the app. Number one, great job working this out on Flask. We haven't discussed Flask at all. So you probably had to do a lot of that all on your own and a lot of research. I applaud the effort. Fantastic work. And it works. That's even better. So yeah, again, we're seeing that the random forest model performed a little bit better, probably because we got a lot of non-monotonic or non-linear relationships in the data.
And I learned that because of you just explained it from the last one.
Right, but it bears repeating. So that's awesome. But I do want to touch on something that you brought up. Ethics in data science. So this is a real topic, and at the risk, I don't want to get into a whole long tangent. If you're interested in that, hit me up later, because I can talk about this all night. But the short and sweet of it is this. If something is predictive, if you have a feature that is a demographic, especially of people, right? For instance, race, gender, sexual orientation, right? These are uncomfortable topics that we generally don't like talking about because they can hurt feelings. In terms of data, okay, we have to look at how predictive these things are, right? And ethics does come into play, but it is not black and white. And
it was a very predictive. It actually did play a very heavy role, and it was just too one-sided. So I didn't want to,
Yeah, and in that case, there is no right or wrong in eliminating that feature. if you feel like it's causing your model to do undue discrimination based on some demographic feature, right? A case in point, there was recently in the news an article about machine learning algorithms that were unintentionally biased against people of African American or African descent because for some reason it had weighted that they were less likely to need help, right? And so their priority in like an ER setting was dropped, right? There was like a whole thing about it. And you know, machines don't discriminate, but right, the features that we put in them can cause them to inadvertently discriminate, right? And sometimes that's not what we want. So here's my my stance on this, right? Always include. I would personally always expand or rather explore all of the data that you have, right? Take a look at it. But if I see something that's incredibly lopsided, like if gender suddenly, you know, was like a telltale factor, you can almost make the decision based off gender, right? My first question would be why?
And yeah.
Right? Explore that a little bit. And if it seems like you can't come up with a good explanation for why, then exclude that data, right? To be on the safe side. Or do a you know, make your project two-sided, where you do one with and one without and compare the differences, right? But we do have to be careful about how we do that. And there's a tactful way of doing it. So make sure that you tread carefully in those areas.
I really wish I could have explained. I wish explaining the feature engineering part was part of the blog, because that was my favorite part.
We'll definitely link that. I'd be interested in reading more about your process there. But yeah, I digress. That's a whole lecture in and of itself, I'm sure. We will move on to the next. Thank you, Dustin, for that awesome project. Let's show some love for Dustin in the chat, y'all. Up next is going to be Daniel Schilling. Daniel, are you here?
Present.
Outstanding. Whenever you're ready, the floor is yours.
Alrighty. Okay. All right. So I got into this data set because I'm a Godzilla fan and I play a lot of Monster Hunter, and the fan base has a lot of crossover with Pokemon. So I was looking at Pokemon data sets, and then we had to pick one, so I was here, so I picked it. But while I was discussing projects, it came up that someone had their story be more about the data cleaning process than the process of talking about how you did your predictive model or whatever. So I thought it'd be fun to talk about some like inferred epiphanies I had while doing the data cleaning and feature engineering. So like we can see here that this is like really inaccurate, but Dragon Ice was the most predicted, which would indicate it's super common. And then only one Pokemon has that combination, so this ends up being the very center of the Pokemon combat gameplay system, I guess. Very new to Pokemon. I've only been looking at it for like a week and a half. But this is Kiryu, or Kiryuum. I don't know how to pronounce that. But anyways, when I was looking at that, I thought it would be fun to check out some other things and see if I could find some other interesting correlations. And it turned out that Ice Dragon Pokemon also have the most common body type, apparently. Which is weird because only one of them exists. But I also looked at like life cycle, and we had electric ghost types as being the most commonly predicted, so like most average life, which is interesting to imagine. But getting to a model that actually does something, we got, what's up?
That was the 5-second countdown.
Okay, my bad.
So no, it's okay if you have like one quick thing that you want to add before you wrap up.
Oh yeah. This is like the end of the actual model process. So looking at the combat stats ended up being like the only thing that really got above the baseline average. So I was able to actually get a decent model at 85%, and I did it by making a multi-output function. So I looked at, because Pokemon can have 2 types, so it looks at each type individually, and that ended up being the most accurate way to do it with
Okay, that's interesting. So, all right, definitely a lot to dissect here, a lot of information. I feel like I just learned a lot about Pokemon. That's never a bad thing. So if you had to summarize your project, like what was your question? What was your problem that you were trying to solve?
Well, my initial project, the initial problem I was trying to solve was just to see if you could predict Pokemon types by examining other peripheral data, because Nintendo uses like a very specific design philosophy, and this was the most complete data set that I found, so I was wondering if it would be possible, and I had to do some somewhat creative feature engineering to actually make that work.
Yeah, okay. So like I would be very interested in hearing more about your feature engineering and the model itself. So like while I don't necessarily dislike hearing about the data cleaning process. It was very enlightening. I feel like I didn't get enough of the actual model that you built. I don't really know much about it at all. So that's my only critique. But definitely link your project, and so that we can have take a look at it later. Okay.
Okay.
And fantastic. Thank you for sharing that with us.
Thank you.
All right. Up next, let's see. We have Terrence. Terrence, are you with us?
Yes, sir.
All right. Whenever you are ready, the floor is yours.
All right. Can you see my screen?
Yep, get you loud and clear.
Okay. So for my project, I wanted to predict used car prices based on the car's characteristics. So I went to cars.com and collected data on used cars. And here is the data I ended up collecting. This is just a brief description of how I ended up collecting the data. For cleaning the data was relatively clean. It was just a matter of removing characters in the elements that I didn't want and refactoring the data. And this is a look at the data set after all that was said and done. Exploring the data, here's a correlation matrix. So we want to look at the target vector of price and all the other features. There's a couple of key features that are heavily correlated with price. One being the car year and the mileage of the car. So this is a distribution of the cars by make as well as year. And this is like a distribution of the mileages of the cars. For my models, I'm using the mean absolute error as my scoring metric. And for a baseline, I just use the mean as a general guess. And I got a mean absolute error of about 1,400. Then I created a simple random forest model and got a score of about 980. I did some feature selection. I used permutation importance to narrow down the features that affected the model the most in the positive direction. So I used 13 as a threshold. So all these features were used. I then created another random forest with those features, and then had some hyperparameter tuning and got a score of 960. We can interpret a little bit of the model with car year and the mileage versus price, as well as the SHAP values. And then for a final prediction, we got a score of 950. And then a little bit of what I would do differently next time.
All right, perfect. I'm going to stop you there. All right. So fantastic. This one hits a little close to home. This is actually, I did pretty much the exact same thing, though obviously with a different data set. It was cars at my time and in my area. But this is interesting. All right. So we definitely learned a lot. And I think judging by your scores, right, you're getting it on average within $960 of the actual sale price. And I'm assuming that's the listed price, not the final sell price, right?
Correct.
Yeah. All right. Cool. So yeah, we're kind of honing in on that list price, right? But then $960, that's pretty good. So yeah, fantastic work. I loved the breakdown of your process, the distributions, right? I'm really kind of getting a keen insight as to how you arrived and made some of the decisions that you made. Fantastic work. Thank you. All right. Okay. Up next. Oh, and we actually have, okay, we need to add a person to the list. Here we go. She will be, 1 second. Up next is going to be Sydney. Sydney, are you with us?
Yes, I'm here. It's Adani.
Oh, Sidani, I'm sorry.
Sorry.
Feel free to
Yeah.
correct me. Awesome. All right, so whenever you're ready, the floor is yours.
It's been a little slow today. So.
Mine's slow every day. I understand.
All right. Are you able to see the screen?
Got you loud and clear.
Okay. So my data set, I did it on human trafficking. It seems to be a thing that's been used a lot, and the rate of human trafficking has increased over the years. So I did a tree. I ran a tree regression, and basically it says the decision tree that the type of exploitation that's like most determining of if you're going to be trafficked is sexual exploitation. And then some of my top features at the random classifier was exploitation type, the country of exploitation, citizenship. And then here I did I wanted to see like what significance does age play. And so like the highest, like if you're 0 to 8 years old and 39 plus and 9 to 7. So most predominantly minors are more likely to be trafficked. And I wanted to look at if your relationship to the recruiter played a part, and it didn't really have much of a significance difference. And then here I just did a Shapley plot to kind of compare like one instance of being trafficked. And if you could read about it more. And then here I just kind of did a graph about like the data set, years of from the year 2002 to 2018, amount of people being trafficked and their age.
All right, is that the end?
That's the end.
All right, perfect. So a little under time, perfect, that's fine. Great. So the only one thing that I would love some clarification on with that Shapley plot was that predicting high likelihood of being trafficked or low likelihood of being trafficked?
So that was predicting that if you are being trafficked, the sex exploitation for the United States of America, and the relationship with your partner is not known, you're 7% likely to be trafficked.
Okay, got you. All right, so that's predicting the probability of you being trafficked. Okay, very interesting. So, okay. Yeah, another great case of a project that deals with data can be hard to digest, right? And I feel like you approached it very tactfully, all right, sticking to the numbers and to the data, and that was very well done. I loved your presentation there. I'm kind of surprised by some of the things that I saw, right? Some of the results. And I would definitely be interested in learning some more about that. So in that regard, I very much appreciate all of the model insight that we got from the Shapley value plots and the correlation in PDP. So fantastic work. Thank you, Sydney. All right. Let's show some love for Sydney in the chat. Up next is going to be Ray. Raymond, are you here?
Yes, I am.
Fantastic. Whenever you're ready, the floor is yours.
Okay. So
basing my data set on the public game called League of Legends and seeing if, and within the diamond ranks, if the blue team is winning. So a quick look at the weights. It seems that the goal difference between the two teams is the most weighted on which team will be winning, as shown here as well for the top 20 features. It's definitely going to be the gold, as gold is the most important resource next to experience, since more gold equals better items. And a quick look at the partial dependence plot. It's heavily skewed to the right. So as long as a team is gaining more and more gold, they're going to gain a bigger advantage over the other team. So a quick breakdown on these visualizations show that while it is possible to predict the outcome of blue team winning, is not always true, because within a single round, there can be many other unexpected factors that could turn it from a winning to a losing game.
All right, is that the conclusion? Perfect. So you guys are trying to mess me up with this name thing. All right, so yeah, no, this is very good. And yeah, predicting outcomes of matches, especially in sports, is tricky to begin with. So definitely applaud the effort there. Can you scroll up a little bit on here? So we see some of the other one. There we go. Yeah. So goal difference, that kind of makes sense. As someone who's played League of Legends, that would kind of probably be the biggest tell. But so many times I've seen big comebacks from goal deficits on red team. So yeah, that's gonna be a tough one to tell. But how well did your model do in being able to predict with your sample data?
So it predicted with a 93% accuracy score.
93% accuracy.
Mm-hmm.
Very interesting. Yeah, I would be very interested in seeing a little bit more of the model breakdown for your different metrics. Like that would be pretty cool.
Yeah.
Other than that, fantastic work. Thank you for sharing. All right. Up next is, and I'm going to butcher this, I'm so sorry in advance, Shayna? Shayna, are you here?
Shayna's correct. You got it.
Yes. All right, cool. Yes, perfect. All right, whenever you're ready, the floor is yours.
Okay, so I wanted to predict something a little bit fun. I found a survey on Kaggle of about 1,000 young people, and it asked them questions based on their hobbies, fears, and personal opinions. So I decided I wanted to predict whether or not I decided whether or not I wanted to predict loneliness based on the other factors. The data was fairly easy to work with, as most values were on a scale of 1 to 5, with 5 being highly agree with the survey question. There is a detailed description of all of the survey questions and the categories that I chose on Kaggle if you're interested in looking at those. So I was only interested in the people who reported feeling severely lonely. So I changed it to a binary classification problem, with the 4 or 5 being represented by 1 and everything else being represented by 0. So this resulted in imbalanced classes between 74% 0 and 26% 1. I chose precision as my metric because I was mostly interested in precisely being able to predict whether they were severely lonely. So I did some simple models and came up with the top 20 features. And looking at them, a lot of them are pretty intuitive: happiness in life, feelings about the past, energy levels, friends. A lot of these things we feel can relate to loneliness. So then using those features, I fit a logistic regression model, decision tree random forest, and a gradient boosting model. Compared those to find the best performing one. My random forest and the gradient boosting models gave me the best metrics. So this is a comparison between the random forest and the XGBoost permutation importances, and it split up the variables very differently, which I was surprised by. But despite those differences, they came out with very similar metrics. These are the confusion matrices. I was getting a lot of false positives. RSC scores were pretty low, but then when I came down to the precision metrics, my best performing one was the XG boost, which gave me about an 82, which is fairly high, and I was quite surprised by it.
All right, now let me stop you there. We are at time. Fantastic work. So yeah, this one was definitely different. Predicting loneliness, a complex, very complex whole range of human emotions, right? Definitely not something that's easy, but I see that as being, a project that would maybe have a lot of like real life applications as well. So that's pretty cool. Yeah, and I really loved the comparison for the feature importances. I appreciate that because being able to get some insight into how the random forest decided to weight things versus how the gradient boosted model chose to weight things. You can see some little bit small changes, right? But the actual gradient of the effects, right? There was a much greater lean toward the bottom of the list being highly negative versus the top of the list being positive as compared to the random forest, right? And without going into too much specifics, I would imagine that probably has something to do with why it was had slightly higher predictive capability. So that was fantastic. Thank you very much. All right.
Thank you.
With that, because we saved the best for last, we are done. I have no one else on my list. Does anyone here think that they should have presented but did not get called and would like to do so now? No volunteers? All right. No one wants to go again just for Eagles? No, I'm just kidding.
Paul said he wants to go again.
Paul? Yeah, come on, Paul. No, just kidding. Fantastic work, guys. Listen, regardless of how you think you did, right? You spent the last 2 weeks working on this, and the effort really showed through, right? Great work. And what you've accomplished here is definitely something that you can be proud of. On an ending note, I want you all to reflect on where you started from versus where you are now, right? Remember back to day one and just think about the changes that you've made and the knowledge that you've gained, right? You guys have a lot to be proud of. These projects, so like they were amazing. All of them were really good. All right, fantastic work. Give yourself a pat on the back, right? This is no easy feat, and definitely something you should be proud to show off. So make sure you put this on your portfolio. Tying up, make sure you have until the end of 5th day to get all of your deliverables wrapped up, folded neatly, and handed into your Monday through Thursday main TL. If you did not present today and you're here, you will need to present on your 5th day if possible. Okay? But make sure you get your all your deliverables turned in. Check your rubric. The link for that should be pinned in the main channel. If it's not, I will drop it. Otherwise, great work, everyone. Fantastic. Be proud of yourselves. I really loved what I see. I liked a lot what I saw tonight. With that, thank you everyone for sticking around. It's been almost an hour and a half.
Hey, Brandon.
Yeah.
Is there a retro for them?
Yes. Okay. So on your 5th day, before end of day 5th day, there is a sprint retrospective that you'll need to fill out. It should be for build week, unit 2 build week. I will confirm that. But yeah, you will need to fill out a sprint retrospective for the build week. So make sure you get that turned in as well. Thank you for reminding me. All right. I've got nothing else. Thank you everyone for coming and sticking around till the very end. Have a great night and breathe a sigh of relief. You're done. We move into unit 3 starting Monday. I will see you all there. Ciao for now.